Welcome to an introduction to proof by induction. Mathematical induction is a proof technique. In other words, induction is a style of argument we use to prove that a mathematical statement is always true. Many mathematical statements can be proved by simply explaining what they mean. Others are very difficult to prove. In fact, there are relatively simple mathematical statements which nobody yet knows how to prove. To facilitate the discovery of proofs, it is important to be familiar with some standard styles of arguments. Induction is one such style. Proof by induction is useful when trying to prove statements about all natural numbers or all natural numbers greater than some fixed first case. In particular, induction should be used when there is some way to go from one case to the next when you can see how to always do one more. Thinking about a problem inductively can give a new insight into the problem. When asked to provide a proof by induction, you are being asked to think about it dynamically. How does increasing n change the problem? But there is another side to proofs by induction as well. In mathematics, it is not enough to understand a problem, you must be able to communicate the problem to others. Mathematics has standard language and style, allowing mathematicians to share their ideas efficiently. Proofs by induction have a certain formal style. It allows us to keep our ideas organized and might even help us with formulating a proof. Here's a general structure of a proof by mathematical induction. We start by saying what the statement is that you want to prove. Let P of n be the statement. To prove that P of n is true for all n greater than or equal to 0, you must prove two facts. Number one, the base case, prove that P of 0 is true. Do this directly and is often very easy. Second, the inductive case. Prove that P of k implies that P of the quantity k plus 1 for all k greater than or equal to 0. That is, prove that for any k greater than or equal to 0, if P of k is true, then P of the quantity k plus 1 is true as well. This is the proof of an if-then statement, so you can assume P of k is true. P of k is called the inductive hypothesis. You must then explain why P of the quantity k plus 1 is also true, given that assumption. Assuming you are successful on both parts, you can conclude, therefore, by the principle of mathematical induction, the statement P of n is true for all n greater than or equal to 0. Sometimes the statement P of n will only be true for values of, for example, n greater than or equal to 4 or some other value. In such cases, replace all the zeros above with 4s or some other value. The other advantage of formalizing inductive proofs is it allows us to verify that the logic behind this style of argument is valid. Why does induction work? Think of a row of dominoes set up standing on their edges. We want to argue that in a minute, all the dominoes will have fallen down. For this to happen, you will need to push the first domino, that is the base case. It will also have to be that the dominoes are close enough together that when any particular domino falls, it will cause the next domino to fall. This is the inductive case. If both conditions are met, you push the first domino over and each domino will cause the next to fall, then all the dominoes will fall. Let's look at an example of a proof by induction. Let's prove that for 1 plus 3 plus 5 plus ... plus the quantity 2n minus 1 equals n squared for all natural numbers n greater than or equal to 1. To begin the proof, for each n, let P of n be the statement 1 plus 3 plus 5 plus ... plus the quantity 2n minus 1 equals n squared. Next, we have the base case, in which we show that P of 1 is true because 1 equals 1 squared. Now we need to prove that if P of k is true, then P of the quantity k plus 1 is true, as well as for all k greater than or equal to 1. So for the inductive case, we let k be a natural number where k is greater than or equal to 1, assume that P of k is true, which is 1 plus 3 plus 5 plus ... plus the quantity 2k minus 1 equals k squared. Now we consider P of the quantity k plus 1 by adding 2k plus 1 to both sides of the equation. We get the true equation 1 plus 3 plus 5 plus ... plus the quantity 2k minus 1 plus the quantity 2k plus 1 equals k squared plus the quantity 2k plus 1. If you're wondering where the 2k plus 1 came from, notice in the statement P of k, the last term on the left side of the equation is 2k minus 1. If we replace k with the quantity k plus 1, The last term is 2 times the quantity k plus 1 minus 1, which is 2k plus 1. Also notice on the right side, we have k squared plus 2k plus 1, and this is key because if we factor this, notice how we have two factors of the quantity k plus 1, which we can write as the square of the quantity k plus 1, which is what we want to show p of the quantity k plus 1 is true. Since the right side of the equation is equal to the square of the quantity k plus 1, we have 1 plus 3 plus 5 plus ... plus the quantity 2k minus 1 plus the quantity 2k plus 1 equals the square of the quantity k plus 1. This is the true statement p of the quantity k plus 1, completing the inductive case. Therefore, by the principle of mathematical induction, the statement p of n is true for all natural numbers n greater than or equal to 1. Before we go, here are a couple extra notes. In order to prove the inductive case, you have to first determine what the conclusion should be, for example, what p of the quantity k plus 1 looks like. Number 2, you can think of p of n as a sequence of statements and p of the quantity k plus 1 as a recursive definition in terms of p of k. When you are asked to prove a statement by mathematical induction, you should first think about why the statement is true using inductive reasoning, explain why induction is the right thing to do, and roughly why the inductive case will work. Then sit down and write out a careful, formal proof using the correct structure. I hope you found this helpful.